Hello, my name is Elizabeth Torres. I'm an associate professor at Rutgers University and the psychology department, and I'm going to be talking today about stochastic shifts in learning performance across the lifespan. Human performance is quite complex, and in recent years, we've been able to leverage the wearable sensor revolution to go beyond human observation into a higher level of granularity um, involving the activities, the self-generated activities from the nervous systems that these sensors can record. However, with this new technology, we have noted several challenges using the time series data that the sensors offer. Among them are multi-layered and multimodal data, different sampling resolutions, different time scales and frequency sampling scales, different physical units from different types of sensors, data loss owing to grand averaging techniques under a priori assumptions of certain probability distributions, the presence of different anatomical sizes that impact the motion that the sensors collect, and the need for a standardized waveform that can be integrated across different layers of these multimodal systems. And in particular, the shifting age-dependent probability landscape that arises from the different signatures of variability that we explore under different contextual situations. An example of these challenges is used here to illustrate some of the problems using the hand speed motion, the linear speed of the hand derived from movements to a target, to an instructed target. And what is typically done is a superimposition of epochs from the data defined by specific behavioral landmarks, and a grand averaging under an assumed theoretical mean, which then incurs in loss of gross data and throws away important fluctuations, what turn out to be important fluctuations, as noise. Our approach is different in that we take a continuous time series data, say across the day or different days or so on, and take sliding windows that where we track the fluctuations away from an empirically estimated mean, which shift over time, and considers these fluctuations in the amplitude of the peaks or in the time inter-peak time intervals in the data. And then from there, we derive a standardized waveform spanning from 0 to 1, unitless, which takes care of allometric effects owing to different anatomical features across different subjects and different ages, different states of maturation, and we call these the micro-movement spikes. Spikes because we derive them from the peaks in the raw data. And we apply these to all sorts of different sensors, different biorhythms from the nervous system. We then group them in a frequency histogram and use maximum likelihood estimation with high confidence, 95% confidence intervals, to estimate rather than assume an empirically derived continuous family of probability distributions functions. In this case, we've found that the gamma family does a good job at characterizing human performance in general. And in this way, we shift from a one-size-fits-all approach with a grand averaging under some statistics to a personalized model that specifically tailors the analysis of behavior to these stochastic signatures that are unique to each individual. These movements are quite overt and visible, and we can describe them visibly by observation, but there are a number of family of movements that are occur largely beneath awareness, and we can't and beyond the detection of the naked eye. And one of them, for example, occurs quite often when people try to curtail their movements in the magnet during the resting state of fMRI data. And by now there are open access databases that provide this type of data for analysis. And so in seemingly resting state, where there is quite a lot of motion of involuntary movements that we can also analyze using the micro movement spikes approach. So we take, for example, a child, a neurotypical child and an autistic child, and we can see profound differences in the amount of motion that their body outputs and that the head registers. And using the micro movements approach, we can then estimate the stochastic signatures using the gamma probability family, and plot each child in a gamma parameter space spanned by the shape and the scale of the distribution. This is upon gathering all those peaks in frequency histograms and fitting using maximum likelihood estimation. And using the shape and the scale, we can then plot these points in a gamma moments parameter space and study large cohorts as they stratify. We can take these micro movements as vibrations and convert them to sound and play them back to the system and examine in closed loop and causally how that type of music, which is system self-generated, influences cognitive activities and do so at other layers of neuromotor control, including the autonomic nervous system here instantiated by the EKG signal time series that we can extract the micro movements from the R peaks and examine them under different levels of cognitive load. We can go beyond time domain analysis into the frequency domain analysis and examine how the brain is sensing these vibrations kinesthetically, and explore different frequency bands that haven't been explored, because now we have, with the wearable sensors revolution, we have high sampling resolution that we can further go beyond what we know about the physiology of the motor system. We were inspired by the original work of von Holstein and decided in the 1950s. And in their own words, I quote that voluntary movements show themselves to be dependent on the returning stream of afferents which they themselves cause. This is known as the principle of reafference and of kinesthetic reafference. And what we have non-trivially added to it is a set of movements that occur largely beneath awareness, that are not necessarily voluntary under voluntary control, but that contribute, we hypothesize, to action, to the emergence of action ownership and the sense of agency in precognitive states of infancy, and that enable the brain to understand cause and effect. And so we can, using this approach, shift from a completely correlation-based analysis to a causation analysis, and understanding how the nervous system interacts with the environment and how intelligent behavior self-emerges autonomously. We pair this paradigm with the phylogenetic taxonomy of motor control maturation, a study in both top-down influences and bottom-up influences from the peripheral nervous system to the central nervous system, and map those levels of voluntary, involuntary, and autonomic control to three fundamental types of muscle tissues that innervate, that occur across all organs in our body and are responsible for voluntary, involuntary, and autonomic control, and that have a specific genes expression to it. So in this way, we have connected all the way from complex performance to phenotypic behaviors to tissues that have genomic and proteomics expression that we can quantify all within the personalized medicine approach. An example of an experimental assay that we have used in autism is a simple pointing paradigm which we illustrate here in the simplest biomechanical form, a baseline state of going, bringing the hand to the target upon instruction, and then without instruction, spontaneously retracting the hand. And so we have two phases, the deliberate and the spontaneous phases, contributing differently to the feedback that we get from the kinesthetic reafference. And elaborating some more this paradigm, we add a match to sample task, we add the layer of decision making with different levels of cognitive load that influence our motions. And we can see here the evolution of the cognitive load that cause motor learning and adaptation. And over practice, we can then study how the system adapts and how the system learns and how the system becomes better at decision making, better accuracy, better timing, and so forth, both in neurotypical and in autistic children. Here's an example of a minimally verbal autistic child who learns to perform this task, first with a lot of support, and eventually with self-volition, self-initiating the movement, and with high autonomy. So in the initial stages, we teach the child all types of things involving eye-hand coordination and the mapping between a stimulus response, but more importantly, we teach them the sensory consequences of his self-generated actions and of the actions that he receives support from. We do this in the context of reinforcement learning, where we reward the child after every trial, and then after a few weeks, the child performs this task on his own, entirely self-volition. So his intent is now mapped to his volitional control, and it's a very rich setup, so we can study both decision making continuously beyond mouse clicks or binary states as a continuous random process. Here is an example of hand trajectories en route to the target and away from it, studying the deliberate and the spontaneous motions automatically extracted from the continuous stream of data. And so we look at the peaks and valleys. And when we gather them in a frequency histogram, we see fundamental differences between the typical and the autistic system. In particular, the autistic system, we discovered that it has the presence of the memoryless random exponential distribution. And then we further align the movement to the touch and plotted the speed profiles, and realized that when we stock up all these 100 trials that the child performed, in the typical case, there is a high predictability, there's periodic behavior whereby previous events can be used to anticipate impending events. And this is not the case in autism, where we have the presence of high randomness and high noise. And so this is a system with high uncertainty, and in the framework of kinesthetic reafference, the system cannot possibly feel at ease. We can safely infer that given the high uncertainty. We then study this continuously as a continuous waveform throughout the day, and we can track the stochastic shifts using the gamma probability distribution, which does a good job at modeling empirically the human performance data. And in this sense, we have sampled by now thousands of individuals and characterized the gamma probability parameter space of shape and scale, examine the noise to signal ratio, which happens to be the scale or the dispersion parameter of the gamma, and discover that this should be our target for interventions in autism and in other disorders of the nervous system, because here's where the neurotypical system is aiming for: symmetric distribution with low noise to signal ratio, enabling the prediction of impending sensory consequences to compensate for internal sensory motor, sensory transduction, transmission delays. We then have the opportunity to carry on a cross-sectional study from 3 to 25 years of age and examine the trajectory of maturation of the nervous system in terms of the noise to signal ratio and the types of distributions that we see, and it found out that in the typical development from 3 to 4 years of age, there is the presence of the exponential distribution, but this shifts around school age into a fundamentally different regime, and by college there is a symmetric distribution quite common, but in autism this is not the case, and we can see this represented in the log gamma shape scale parameter, which spans a power law, as it turns out, representing the maturation of the nervous system and localizes each age group quite distinctively in the typical case, but not in the autistic case. Here we can characterize empirically the different regimes, and in autism they are absent, and so we can define a target for treatment in using the noise to signal ratio, which we have obtained proof of concept for in an intervention that is beyond the scope of this work, but you can ask me about it if you so desire. This work defined a maturation path in humans, define a target for treatment in an age-dependent probability space in ASD. Now, this is under voluntary control, but how about involuntary movements that are beneath awareness? So we went back to thousands of participants in resting state fMRI and discovered that indeed there is a systematic shift in noise to signal ratio and towards the exponential random distribution with the use of psychotropic medications. And in addition to that, we examined thousands of individuals from 5 to 65 years of age and discovered that they have different stochastic trajectories on the gamma moment space. And by the age of 40, there is a large departure from the neurotypical nervous system. And indeed, the literature reports that there is a high incidence of Parkinsonism after 40 in autism. So in conclusion, I have presented to you a new standardized data type, the micromovement spikes, a new taxonomy of phylogenetic maturation empirically tested, a new personalized method of a stochastic analysis, and an age-dependent probability landscape revealing target for treatment in autism. And in general, we offer a unifying framework to study human performance across the lifespan. I want to thank our multiple sources of funding and our prior students and postdocs and our current members of the lab. Thank you for attending our talk.